Morning everyone. Today's topic for seminar is MRI Physics. So I'll be starting with the MRI machine and explaining about the coils, then go for MR active nuclei. Then I'll talk about spin, precession and resonance. Then concept of T1 recovery and T2 decay. So till here it was about the contrast formation. Then I'll talk about how to capture the image using slice selection, frequency and gradient encoding. And then talk about the basic pulse sequence. So coming for the MRI machine, the MRI system consists of a MR console and a computer system. So operator or a technician from the computer system controls the radio frequency transmission and gradient power supply, and the image is captured. Once the image is captured from the MRI system, the radio frequency, after the radio frequency is received, the image will be captured, and digital format of the image is reconstructed and displayed in a computer image. So this is a MRI console. It consists of an MRI machine, and the bore is also called gantry, within which the patient lies on the table. And it contains magnets in the outermost diameter, and then as we go inwards, it contains different coils. The outermost being the main magnetic coil, then the gradient coils, and the innermost is the radio frequency coil. So coming up to the various coils of MRI machine, there are mainly four types of coils within the MRI machine: main coil, shim coil, gradient coil, and radio frequency coil. The one blue color is the main coil, the purple one is the gradient coil, the longitudinal ones are the shim coils, and the yellow one is the radio frequency. So main coil, it generates the longitudinal magnetic field, the main magnetic field along the z-axis. Z-axis passes through the patient, the longitudinal axis, from head to toe. Then comes the gradient coil. It generates the gradient across the magnetic field. Then shim coils. It reduces the magnetic field inhomogeneities. The magnetic field inhomogeneities are created due to MRI properties and machine properties and various environmental effects. So we need to reduce the inhomogeneities to get a clear image. Then comes the radio frequency coil, which generates an RF pulse. So radio frequency coil, it consists of a transmitting coil and a receiver coil. Transmitting coils generates a B1 magnetic field. The B0 magnetic field was created by the main coil. The radio B1 magnetic field is created by a radio frequency coil. And then once the radio frequency pulse is transmitted, and then it has to be received also to create a signal. So it is received by a receiving coil. So this is the head coil. The RF coils can be embedded within the MRI machine, or it can be there as a separate coils, which is in close proximity to the body. So coming to the MRI magnets, most of the MRI systems use superconducting magnets. What is a superconductor? A superconductor is the one which has very less or almost no resistance to the flow of electric current. The main advantage of using a superconductor is it reduces the heat produced, and with less number of loops it can create more stronger magnetic field. So a typical magnet in an MRI machine consists of a small niobium, titanium and copper alloy. So copper is needed to produce little electric resistance, and it also functions as an insulator around the alloy of niobium and titanium magnet. So what are the MR active nuclei? In our body, it majorly consists of oxygen, hydrogen, carbon and nitrogen, which make up 90%, 96% of our body mass. Most of the body mass is taken up by oxygen, but in number, the most of the atoms in the human body are of hydrogen atoms. So MR active nuclei are carbon 13, fluorine 19, phosphorus 31, nitrogen 15 and oxygen 17. They have the ability to interact with the magnetic field. Why is it? Because they contain an unpaired electron in the nuclei, which can act as a tiny magnet and interact with the magnetic field. So hydrogen is the most commonly used MR active nuclei in clinical practice because it has a solitary proton, and which gives it a large gyromagnetic ratio, and it is abundantly present and positively charged and has a spin. So MR utilizes the magnetic spin property of these protons and generates an image. So does that mean we are magnets and can we act like magnets? The answer is no, because the protons in the body are spinning in a haphazard manner. They are not in phase. So they cancel out the spins and the our body will not interact with the external magnetic field. When an external magnetic field is applied like E naught, all of the spins are either arranged in parallel direction or anti-parallel direction and they interact with the magnetic field. What is a spin? Spin is rotation of protons around its own axis. This is a spin, rotation of protons around the own axis. And the rotation of the axis is called precession. So the precession, the speed with which the precession rotates is called precessional frequency or Larmor frequency. One analogy we can take is of a spinning top. So spinning the top is also spinning along its own axis and also spinning with a precession. So that creates a cone. So Larmor equation is given by this formula. Omega naught is equal to magnetic field V naught and lambda, where omega naught is the Larmor frequency, lambda is a gyromagnetic ratio which is specific to the nuclei, and V naught is a longitudinal magnetic field. So the more the intensity of the magnetic field, the precessional frequency will also be much stronger. Coming to the concept of net magnetization, when a B naught or the longitudinal magnetic field is applied, the protons align along the magnetic field. They can be in parallel direction or anti-parallel direction. So the ones which align themselves in parallel direction are called spin down nuclei, or else, in other words, they have less energy, so they cannot oppose the main magnetic field and are aligned in the direction of the main magnetic field. The ones which have the energy to oppose the main magnetic field align themselves in anti-parallel direction. They are called spin-up nuclei. So this is the sum vector. In when a main magnetic field is applied across the z-axis, only that is persistent. So the magnetic field is only we get magnetic field only in z-axis in the beginning. So the longitudinal magnetic field which is applied across the long axis of the body is not measurable because uh, in physics we have learnt about the Faraday's law, where when a electric current is passed across the coiled loop of wires, it generates a magnetic field. So in the same way, when a moving magnetic field is passed across the loop of wire, it should generate an electric current. So it has to be in perpendicular direction to the flow of current. So here the main magnetic field is stationary and also it is not in a perpendicular direction. So longitudinal magnetic field cannot generate an electric signal. So what we have to do is we have to shift the magnetic field from longitudinal direction to the transverse direction in XY plane. So how do we do that? We do that by giving an external energy which gives the which excites the proton to shift their main magnetic field from longitudinal axis to the transverse axis. So the process by which external radio frequency pulse can be given to the hydrogen atoms is called resonance. So using this analogy of a swing, where when a person pushes the person on the swing, the uh, frequency of the swing should be matched with the frequency of the person who is pushing. So the person can go to the highest altitude. In the same way, if we have to transmit the maximum amount of energy into the nuclei, the external frequency, the frequency of the radio frequency pulse has to match with the Larmor frequency of the spinning nuclei. So when an external radio frequency pulse is given, the nuclei which are in spin down state will gain energy and they'll go into the spin up state. So as the frequency is applied, the number of spin up nuclei will increase compared to spin down nuclei and will start opposing the main magnetic field, and they shift their magnetization from the longitudinal axis to the transverse axis. So the transverse magnetic field which is created is called T1, and we give radio frequency pulse at 90-degree direction, so it is shifted from z axis to the xy plane. So longitudinal magnetization, it is basically due to the spin of the nuclei, and transverse magnetization is basically due to precession. But in longitudinal magnetization, the spin of the nuclei overpowers the precession. So mainly we get longitudinal magnetization. The transverse vector in the longitudinal axis will not be present because due to precession, they'll be spinning. The precession of the hydrogen nuclei will be out of phase. They'll not be in phase. So they cancel out each other, and only the spin will give the longitudinal magnetization. When we apply an external radio frequency pulse, magnetization occurs in the transverse direction. So slowly from the z axis, it will shift to the xy plane. So two things happen at the resonance. One is energy absorption, as I've told before. The spin down nuclei will get a spin up state, and then all the nuclei which were out of phase before, they were already spinning in their own axis, but they are not spinning in phase. The precession was out of phase. Now, when we give an external radio frequency pulse, along with the energy absorption, they'll all start precessing in the same phase. So that generates a signal. And then we place a coil in a perpendicular direction to the magnetic field, so that can generate a signal, that can capture the signal. The received signal will be sinusoidal in nature. Once the signal is received, the computer converts mathematical data into an image using a process called Fourier transformation. The emitted energy is very small to convert them into images, so repeated on and off sequences are used. The emitted energy is stored in an imaginary K space, which can be later converted to images. So coming to the concept of relaxation, now the magnetization is shifted from longitudinal axis to the transverse axis. So when we switch off the radio frequency pulse, there'll be no more extra energy given from outside. So the net magnetic vector again transverse is changes its direction from transverse axis to the longitudinal axis. So when that happens, hydrogen protons return to the V naught, the longitudinal magnetic field, and release excess stored energy. The energy is released as heat or exchanged and absorbed by other protons. So when net magnetic vector recovers and aligns across the original or longitudinal magnetic field, it's called T1 recovery. So it is the gaining of the longitudinal magnetic field. So when nuclei lose precession and dephase, it's called T2 decay. So it is losing of the transverse magnetic field is called T2 decay, and gaining of the longitudinal magnetic field is called T1 recovery. T1 relaxation. T1 is the time taken for 63% of the magnetic 63% of the gain of the longitudinal magnetic field. So it determines the T1 weighted imaging. T1 recovery mainly happens due to spin lattice interaction, and the same way T2 decay also happens due to spin-spin interaction, which is 63% of the loss of the transverse magnetization. So fat has very short T1 time and it relaxes rapidly, and water has a long T1 time. So if we keep the TR time very short, the contrast between these two will be very less. So if we keep TR very long, again the contrast will be less. So T2 decay mainly happens due to spin-spin interactions, and it is also affected by magnetic field inhomogeneities. T2 decay is the time taken for 63% of the transverse magnetization to be lost. So due to spin-spin interactions, the magnetic field will not be uniform across the magnetic MRI scanner. So the loss of the transverse magnetization will not be in the ideal manner. It happens rapidly than we think. So Different tissues have different T2 and dephase at different rates. Fat has a short T2 and water has a long T2, as we can see. Fat decays faster and water decays, decay of transverse magnetization of water molecules takes a longer time. Flip angle, it is an angle to which net magnetic vector moves as a result of radio frequency excitation pulse. The amount of rotation or the flipping depends on the strength and duration of the radio frequency pulse. Coming to the concept of time to repetition, it is a time between the application of two radio frequency pulse. The time to repetition determines the amount of longitudinal relaxation that is allowed to occur before applying the next radio frequency pulse. So TR, time controls T1 relaxation. TE, or time to echo, is a time between the application of the radio frequency pulse and generation of the maximum MR signal. So controlling the TE also controls the amount of T2 decay that needs to happen. So TE controls T2 decay. So contrast formation of an image, it is basically affected by two parameters, the extrinsic parameters and the intrinsic parameters. Extrinsic parameters include TE, TR and the flip angle, which we can control from external source. The intrinsic parameters are T1 recovery, T2 decay and proton density, which is inherent property of those MR nuclei. So proton density imaging, we use short TR and long TE. For T1 weighted imaging, short TR is used and short TE. So short TR and short TE, so it will give maximum contrast. This is a T1 weighted image of a brain axial section where we can see the fat which is present in the myelin or the fat which is present in excess in white matter is giving hyperintense signal compared to the gray nuclei which is giving intermediate signal, and water which is present inside the CSF is giving a dark signal. This is a T2 weighted imaging where we use long TR and long TE. Long TR and long TE will give maximum contrast compared to short TR and short TE here. So this is a T2 weighted axial image of the brain where the fat which is present in white matter is appearing dark and the water will appear bright, which is in the CSF. So now we have got the image. Now we have to capture the image. So how do we do? We have to capture the image in three axes: Z axis, X axis, and Y axis. Because in the computer image, each image, the pixel of the image will have three components in X axis, Z axis, and Y axis. So along the X axis, we do it by slice selection, and along X axis by frequency encoding, and along Y axis by phase encoding. So slice selection, radio frequency excitation pulse is applied simultaneously in the linear magnetic field gradient in the direction of a desired slice. It's along x-axis. Slice selection we can do it by three ways. One is by moving the patient along the magnetic inside the bore. So depending on the parts need to be imaged, we can move the patient along. And second is by changing the strength of the radio frequency pulse. And third is by applying the gradient magnetic field. So here the magnetic field gradient is applied where in the right side coil the current strength of the current is more, so it generates a much stronger magnetic field compared to the left side. So here when we are doing slice selection, if we are applying radio frequency pulse at a higher intensity, it generates the image contrast of this part of the body. If we reduce the radio frequency pulse, the image contrast will be shifted to the left side. So by controlling the strength of the radio frequency pulse, we can select the part to be imaged along the z-axis. And we can also select the slice thickness by increasing the bandwidth, the range of the radio frequency pulse. By varying that, we can also increase the bandwidth and increase the slice thickness to be imaged. Second is phase encoding. It is done after excitation and prior to the formation of a signal echo. The gradient magnetic field is applied along the y-axis here. So each point in the y-axis will be experiencing different magnetic field, and because of the different magnetic field, they'll be spinning in different frequency. So that generates an image contrast along the y-axis. Frequency encoding. The same concept, the magnetic field gradient is applied along the x-axis. So along the x-axis, each the MR nuclei will be experiencing different magnetic field, and likewise the different spinning. So we can generate an image contrast along x-axis also. So in the end, along the x-axis, the different intensities of the magnetic field will be converted into different grayscale images. So when we combine all the three axes along z-axis, y-axis, and x-axis, that generates an image. Coming to the basic pulse sequences, I'll be telling about spin echo sequence, gradient echo, then turbo spin echo, then inversion recovery, which includes stir and flare images, then susceptibility weighted image. So spin echo, as we have seen in during the T2 decay, the decay happens much faster than we think because of spin-spin interaction and magnetic field inhomogeneities. So before we can actually capture the image, the dephasing will be very fast, and we are not able to capture the image that fast. So what we can do is we can again create a magnetic field or an echo using spin. So the rephasing, after the dephasing is over, again we'll start rephasing. So that is called an echo, which is used to recover dephasing due to all the effects of spin-spin interactions and the magnetic field inhomogeneities. So when an RF pulse is given, all the precession will be in phase. So as the dephasing starts, they'll start dephasing, and they'll be at different speeds. So as the dephasing starts, the MR signal intensity will reduce and slowly it will be lost. So what we can do is we can apply a 180-degree RF pulse. So instead of dephasing, they'll now start rephasing again. So we can take the analogy of this picture where we have in a circular track, we have a tractor, then a normal car, and a sports car. So at when we apply 90-degree RF pulse, all of the three will start to move along the circular track. Sports car being the fastest, it will move the farthest distance. Then comes the normal car, and the tractor will be the slowest. So if we apply 180-degree RF pulse and tell them to reverse the direction, they'll be moving the same speed. So they'll also reach again at the same point at the same time. So we'll get the higher signal again, and we can capture the signal again in this format. So this is called spin echo because we are using the spin and we are reversing the spin. So it's called spin echo. Now coming to the gradient echo. The same concept, we are doing 180-degree spin using by changing the magnetic field. So this here the bore contains the same magnetic field across the magnetic bore. Then we apply a magnetic field gradient where at one on the right side the magnetic field will be stronger than on the left side. So here the precession will be stronger than the precession on the left side. So the stronger precession on the right side, and the weaker precession on the left side. So now we completely reverse the gradient. On the left side, the magnetic field is stronger now, and on the right side, the magnetic field is weak. So when the precession is shifted completely to like we reverse, the precession, the spinning also reverses totally from right to left. And when the spinning reversal happens, in the middle, at one point, all of them will again come and generate a single image. Like they'll give a maximum signal. So we can use this property to generate the gradient echoes. Coming to the concept of turbo spin echo, this sequence uses 90-degree radio frequency pulse with multiple 180-degree pulse sequences. So in one same TR time, we are using 180-degree multiple times. So the data are used to create a single data set. Multiple rows of raw data are filled during using one single TR period. This allows pulse sequences to be run fewer times and saving the imaging time and faster. Coming to the concept of inversion recovery, here instead of applying 90-degree RF pulse in the beginning, we apply 180-degree inversion pulse in the beginning only. So the precession will be completely reversed and it goes in the minus z direction, and then we allow them to dephase. So from minus z direction, they'll start slowly coming into the plus z direction because the main magnetic field is in the plus z direction. So And when the dephasing happens, we know the time taken for the fat and the water when they approach the zero magnetic field. At the exact same time, we apply 90-degree pulse. So suppose we want to suppress the fat images. So when the fat approaches the zero magnetic field, we apply the 90-degree RF pulse. So fat being at zero magnetic field will not experience any RF pulse. So it will remain constant. But water being at a lower position will experience a 90-degree field and it will get enhanced. So fat in that way is suppressed and water image contrast is generated. Same concept can be applied for flare also, where we suppress water signal. The point when the water TR reaches the zero magnetic field, we apply 90-degree RF pulse. So fat will keep on going, but the water, this signal will not be generated and it will remain constant. So this is how we suppress fat and the water signals. So suppression of fat, the sequence is called STIR, short tau inversion recovery, and suppression of water signals, the sequence is called flare, fluid attenuated and inversion recovery. So this is just explanation of what I've done. The 180-degree pulses causes an initial inversion of the longitudinal magnetic field, which is aligned along the minus z direction. So the magnetization then begins to grow back in the main magnetic field, that is plus z direction. The magnetization of different tissues will grow back at different rates, which is inherent to the nuclei. When the signal from the tissue to be suppressed crosses the zero axis, application of an 90-degree RF pulse will rotate all other signals to transverse plane except the one which is being suppressed. So since the signal from the tissue at 0 point is 0, there is nothing to rotate in the transverse plane. So thus this tissue will not contribute to any brightness in the resulting image. So the time taken between application of a 180-degree pulse initially and the 90-degree pulse later is called tau, also called time to inversion. So if you want to suppress fat that is in stir, we have to keep the tau very short. So this is a stir image where the fat in the back, subcutaneous fat in the back region is suppressed. So once we suppress the fat, we will be able to see the water signals clearly and edema will be very clearly differentiated. This is a flare image where the CSF signals from uh, the water signals within the ventricles will be suppressed. So if there is any edema surrounding the ventricles, we can clearly make out because the water signals from the CSF will be suppressed and surrounding edema signals will not be suppressed. Coming to the susceptibility weighted imaging, this is a sequence is similar to the spin echo sequence except that the initial pulse is less than 90-degree and there is no 180-degree RF pulse. Signal dephasing and rephasing by means of gradient pulses results in formation of a gradient echo, which is used to produce T1 or T2 weighted images. The paramagnetic, dimagnetic, and ferromagnetic substances distort the magnetic field and generates the image. Paramagnetic substances include hemosiderin and dimagnetic substances include calcium. So this is used to visualize the hemorrhages and calcifications in the body. So this is a susceptibility weighted imaging where the hemorrhage is very clearly shown because of the paramagnetic substance which is present in the hemosiderin. It distorts the magnetic field and it causes loss of signal here. So coming to the summary, the structures which appear bright on T1 is fat, melanin, protein-rich fluid, hemorrhage in subacute hemorrhage, slowly flowing blood, paramagnetic substances including gadolinium, copper, and manganese. Then dark on T1, edema, tumor, infection, and inflammation. Hemorrhage, the hyperacute and acute hemorrhage. Low proton density, calcification, and the flow void. Structures which appear bright on T2 are edema, tumor, infection, inflammation, subdural hemorrhage, extracellular methemoglobin in late subacute hemorrhage. Then dark on T2, low proton density, calcification, the fibrous tissue like sclerosis, calcification, the bone cortex will appear dark on both T1 and T2. Likewise, fat will appear bright on both T1 and T2. Paramagnetic substance, deoxyhemoglobin, intracellular methemoglobin, ferritin, hemosiderin, and melanin, protein-rich fluid, and flow.